Okay, next I'll run through the two revision worksheet, one on ellipse and the other on a hyperbola. Okay, so for the first question, um, part one, no problem, part two as well. But when it comes to using the integration to evaluate the area bounded by E, so I think in this case here, we can see that, right, the ellipse is actually one that is stretched vertically, right, with a center, right? The center here was actually, uh, let me see, it was actually 4, 6. It was actually 4, 6. Okay, so I think most students actually retain the ellipse as it is here, and you try to integrate to find the area under the upper part. So that means you try to find this area under the curve for the upper curve, and then you subtract the area of the rectangle below it, and then you times 2. So this is the most common approach I've seen. But I think a good solution would be one that involve, I mean, the most efficient solution is one that involve actually translating, right, the ellipse to the origin as a center, because the area is preserved, right, under translation. So that makes actually the equation of the curve a lot simpler, right? So it's just if you use Cartesian, so one way is to consider Cartesian equation. So it's so minus off the 4, 6, right? You get a simple equation of x squared over 9 plus y squared over 25 equals to 1. So with that, okay, we still need a substitution, right, to do the job. So the better method will be one to translate the parametric equation. That means you strip the right. That means you strip the 4 and the 6 of this parametric equation. So it would be one that is centered at the origin, right? And then you do a substitution using the parametric equation. So that saves you the hassle of actually doing a substitution and coming up with this substitution of x equals to 3 sine theta or 3 cos theta. So that way you will also end up with 15 pi, right? And I think some of the students remembered during tutorial that we actually established this result that the area bounded by the ellipse is given by pi AB, right? Dependent on actually the values of A and B. So yeah, if you check this out, so this is 3 times 5 times pi, right? Okay, so that's the first question. Okay, let me see. Okay, question 2. Okay, interesting how actually complex number, right, come into this chapter over here. But I think you can understand the geometrical implication of modulus of a complex number, right? It's a distance of the point representing the complex number from the origin. So therefore, if you look at this complex equation, right? Right, what it means is that the point representing z, right, the distance. So that means if this is a point representing z, so the distance mod z means this distance mod z, right? Sum with another distance z minus mod z minus 1 minus I. So 1 minus I is probably another point somewhere here. So this is 1, 1. So the distance, right, these two distance are the same. Add up to give you 2. Add up to give you 2. So that fits exactly the geometrical definition of actually the ellipse, with these two, the origin, and 1, 1 as actually the focus. So I think you all saw that, right? So I think I need to highlight part 3 here. Okay, so let's take a look. Right, so okay, lectus rectum not a problem. I was just telling the class that there seems little use for this chord over here. Well, it's a chord that passes through the focus point, but I couldn't find any reason why we should be looking at this particular chord. But anyway, it appears very often in conic question, right? So okay, so I think this part was fine. So the only part that I wanted to highlight was the computation of this point, which is furthest away from the origin, right? So this is one of the best solution in terms of beauty and conciseness. Yeah, there are different ways to do it. So this is one. So this student here from a past cohort actually uses transformation involving a complex number. So it's a rotation of, so basically he works out the modulus and the argument, right? So the modulus of this complex number, because if you have the 2 point, right, if you have the 2 focus, so we know that the distance between the 2 focus is 2c, right? And then the distance between this point to this point is actually a minus c. So that will give this distance from O to the furthest point actually C plus A. So that's what the working here is lah, right? And then you can work out the argument. I mean, no need to work out because it falls on the line y equals to x. So therefore the argument is pi over 4. So it was able to put it all. So this is your r cos theta plus I sine theta. So that's a very nice way of actually obtaining the furthest point. So alternatively, this is a Howray's solution. So he turned it totally Cartesian. So he let z be x plus iy. So basically it's intersecting with the line y equals to x. All right, so you just dump it in and just solve for x. Yeah, so that's how you actually end up with the coordinate as well. Yep, so that's this question here. Moving on, I think there's little problem with this one, except, okay, so the sketching, all that, no problem. Yeah, I think just a few, I don't know why Kant seems to draw the parabola correctly. Now the question make it very clear that you have to indicate the positions where they are closest to the sun. That means you need to indicate this and this in polar form, so r theta. So you should not be labeling this as a over 2 or negative a over 2 0 because that's Cartesian, right? So it should be a over 2 pi and this one is 5 over 3 0. The quick way of finding the answer to part 3, which is to find the range of A so that the path of Earth and comet never intersect, right? This is, so if you look at the graph, the quick way of seeing it is that it will not, because your A is positive, so this intersection is definitely to the left of the origin, right? Because if they do not intersect, therefore this must be happening, right? So that means this point must go after this other extreme point on the ellipse. So this other extreme point on the ellipse, if you solve it, right, is actually 5 pi, right? 5 pi. So therefore the ellipse, if it will not to intersect, must be having a over 2 at least more than 5. So that's a quick way of getting to the answer. So that's this solution here. A over 2 must be more, because we won't be able to consider this because our A is positive. So it will never come a point whereby your parabola is on this side, right? So that's a quick way lah. But few people saw it that way. So most actually went with the equating the two R and use the constraint on cosine theta, right, to work out the constraint on A lor. Because your, in order not to have solution, so the argument is that your cos theta will be more than 1 lah, if you take the mod of it. So that's how it works. Yeah, so this is another solution that's possible. Okay, this one, question 4, no problem basically with the computation, right? Just that the third law, Kepler's third law, right, basically states that the period of the orbit, the square of this period is proportional to the length of the cube of the length of the major axis. So if I can write it as t square proportional to L cube, right? So we want to compute the period of mass. So therefore, you just using ratio, you'll be able to kill off the k. So there's no need to compute the k. So basically use this idea to, yeah, so the connecting the period of mass to period of Earth directly involving the length of the major axis. So that will give you the values here. Okay. Right. Yep. So for this last question, so usually when it's geometry, oh, this is not the last one, for geometry questions, right, the question will sort of guide you, right? They will guide you to proving whatever they want you to prove. So just follow the guide. Okay, so in this case, we got the x coordinate. So this part wasn't a problem. So in a way, you're also tasked to consider direct the DEF definition, right, to work out PF and PF prime. So there's no problem with this. Even deducing this is also not an issue, right? It's the last part on proving the reflective law. So basically what this ratio says, right, when you have PF over PF prime equals to QF over QF prime. So if you rearrange this ratio, it will say PF over QF equals to PF prime over QF prime. So if you go back to your graph, so what does PF over QF, right? Okay, PF over QF equals to PF prime over QF prime is trying to tell you. right? What is this trying to tell you? PF over QF equals to PF prime over QF prime. If you recall your sine rule, right? If you recall sine rule, right? Sine PF over QF basically is the same as the ratio of sine which two angle. Okay, PF over QF. So PF over QF will be as good as the sine of the opposite angle here, right? Which is PQF, right? Over the sine of, so what's opposite QF is this other angle here, sine of FPQ. So we're saying that this ratio is equal to that. So similarly, what is what is PF prime over QF prime equal? So likewise, PF prime will be, this ratio will be equal to the sine of this angle here, which is PQF prime over the opposite angle, which is sine of F prime QP, right? F prime QP, right? So therefore, the ratio of these sines are equal. Now, sine of PQF and sine of PQF prime. Now, these two angles, PQF and PQ F prime, right, are adjacent angles. So they add up to 180. So if they add up to 180, right, the sine values are the same. So you can construct this off. So therefore, it means this sine is equal to this sine. And because they're both in this case are acute, so the angle has to be equal, right? The angle has to be equal. Okay, and that proves the reflective property of the ellipse. Okay, so it will bounce off any ray that any light ray that emerge from one focus will converge after rebouncing off the ellipse into the other focus. So that is the reflective property, right? Okay, the last part, okay, the last question. Okay, I have given this one is C-Tian solution. Can take a look at this. All right. Yep, you can try to understand the solution. I think her point, hold on, let me see, F1P, okay, extended to meet the point Q. That's a bigger picture. Okay, so P, show that PQ is equals to PF2. To show that PQ, so P is down here, PQ is equals to P of F2. So show that these two distances are the same. Right, hold on, let me see. Extended to meet a Q, show that PQ is equals to PF2. So this is definitely one, not a case where you have to find the coordinates and show that they are equal. So what we can do is that we can use properties of ellipse, right? So we can use properties of ellipse. So if you look at C-Tian's solution, right? So she said that F1PA is equals to F2PD. Okay, let's take a look at that. F1PA, so F1PA equals to F2PD. So F1PA, so where is her A? So I don't think her A is over here. Okay, so her A actually is not the same A as the one that I have here. So her A is actually over here, somewhere here on this side. So she's trying to say that F1PA, which is this angle, is equals to F2PD, which is the other angle, because by the reflective property, these two angles are equal, right? This angle and this angle. So therefore, the remaining angle along the green tangent will be the same. And because this angle, right, F1PA is equal to this angle over here, which is your QPD, right, because it's vertically opposite. So therefore, that makes these two angle equal. So these two are equal angle. So that makes PQ equals to PF2. Yeah, PF2. So that's what you're tasked to show. So it's basically to capitalize on the reflective property. So you approach this using angles, right? Okay. So for part 2 is to find F1Q, right? Is to find F1Q. That means this distance over here. So for this, we will use the idea that the sum of the distances from the foci of point P is equals to constant, and that is equals to 2a, right? That's what she has, right? F1P plus PQ, so that must be equal to 2a. And the last part wasn't well attempted because the question was to find the locus, right? Describe the locus of Q as P varies. Okay, it builds up, so you need to look into the results before this part. So the result before this part was F1Q equals to 2A, F1 being a fixed point and A being a constant. So it must mean that Q will vary in such a way that its distance from F1 is always a fixed value of 2A. So that must point to a circle, right, with center at F1 and radius 2A. So therefore your job is to work out the center, right, the center F1. So she has found F1 negative CA, negative C0, right, and the radius is 2A. So that completes the solution. Now because C wasn't, because some of you gave in terms of CA, right? That means the C is actually AE, something like that. Because E is not, or you give it in terms of C. So these are not expressions present in the question itself. So therefore, give your answer only in terms of the I mean expressions in the question, like in this case here, in terms of A and B, right? Okay, of course, the question usually will make clear lah that what to leave it in terms. But these days, I think A-level questions itself is also not exactly, yeah, they may not state what is it in terms of, yeah, not all the time. Okay, so this is the ellipse revision. Okay, so for hyperbola, the first question, okay, just to emphasize this point that you have to use the definition of E. So when you quote results, right, you need to be careful because here they're pointing you to use only this definition of E, right, to find, yeah, whatever. Okay, so in the solution, okay, so I think the first part wasn't a problem. The point is because I think some of you already assume that your this focus here is actually C, and then you start quoting some result about C in terms of A and B. Yep. Okay, so whereas if you look at this solution, right, it keeps actually applying the definition of E. Okay, so I think in the first place I have used so I argue that in this solution here, the argument is that, okay, first of all, why is it C0? Or in this case, I avoid using the letter C, I use F0. Okay, why is it, first of all, on the x-axis, the focus? Because there's an assumption the minute you say F0 or C0. So I think a brief explanation that because of symmetry about the x-axis, right? If you look at the equation, symmetrical about x, symmetrical about y. But by symmetry about the x-axis, we have actually the coordinate of F to be of the form of F0. Okay, and then if you consider, okay, given the equation of the hyperbola, right, actually there are two known points. There are two known points that you can capitalize on instead of using general point, right? So you will look at point A, right, and point B. So by the definition of E, right, so the distance of A to F, right, is equals to the distance of A to the directrix. So in this case here, I don't even assume the directrix. Yeah, I don't even assume the, let me see. I think you were given the directrix in this case here, right? You were given the equation. Yeah, okay, so you are given this, so I can use this. Okay, actually there's a way to prove it even without not knowing that. Okay, so, yep. So therefore, I'm able to make use of, yep, the distance, right, from the directrix. Okay, so I will end up, if I consider A and B, I will end up with a pair of equation, right? Okay, and by equating, right, them, I'll be able to find F in terms of A, and I can of course find E after that. Yeah, without actually involving C and its relation with A and B. Okay, just purely using E lah. Yeah. Okay, then I think the next part is the usual where we need to derive, right, the polar equation based on focus as a pole, right? So you will draw this diagram. We have some practice in class, right? So basically measure the distance from the directrix. Yeah. Okay, question 2. Let me see. Question 2. Okay, this was okay. Just different. Okay, they are confocal. The basically work out the C and it will work out to be the same. Right, one is an ellipse, one is a hyperbola. Right. So the point to make here is that you have to show that when they intersect, right, they are perpendicular to each other. So therefore, the idea is to find the gradient. That's why we are doing dy dx, right, for both the ellipse and the hyperbola. So the point is to show that at the point of intersection, when you times these two together, it is equals to -1. So we got to equate to find the point of intersection first. So here we have x naught square and y naught square found. You can break it down into four points of intersection, right? But the main thing is actually whichever point you're looking at, the product of this gradient, right, always involve the square of x naught and the square of y naught lah. So therefore, there's no need to break it down so fine as to find x naught and y naught and to throw in. So the product involving x naught square, y naught square will always be 9 over 16 for this part here. So times it to -16 over 9 will always result in -1. So at whichever of the 4 points that you're looking at, the intersection will always be at right angle. So both this ellipse and hyperbola are orthogonal. Okay. The question 3. The hard thing about conics is that I always feel that there are many ways to do the problem. All right. So some long, some short. Okay, some very elegant and some can be very messy. So the problem is to decide which method to apply, right? So in this case here, I have to show that OQ is equal to I have to show that OQ is equals to 69 units, okay, given all that. So here again, I can use I don't need very much formula. I just need to apply the definition, the geometrical definition that the difference between OQ and QF is the same as the distance between OP and PF, right? This difference is equal to 2A, remember? It's a geometrical definition of ellipse. So this lead to one of the shortest and most elegant answer that we can find for OQ, 69 units, right? So we have this one. But there are different ways that you can do. Some quoted some results, okay? But nothing said, yeah, you can go ahead and apply some of those standard results to do the job. Okay, then for part 2, okay, so this is where I think one of the problem most students have is to find this polar equation with O as the pole, right? With O as the pole. Okay, so what we usually do will be to use the definition here to model, stating the domain. So what we'll normally do is the usual, right? We will mark a general point P, right? And then to define, to define R and theta. And then to use the idea that, okay, in this case here, I used the idea because I didn't involve E. So I used the idea that OP minus PF is equal to the 2A, right, 46. So that gives us this expression involving R and theta, right? So your job is to simplify. So okay, once you have this line, right, rest of it is to actually open up to make R the subject. So we end up with R being like that. Okay, 69 over 2 cos theta minus 1, right? The question mentioned domain. Okay, reason is because we do know that the hyperbola has a asymptote, right? So which means that as you extend the graph, we are going to expect asymptote, right? The graph to be tending towards some kind of a line. So how do we determine this asymptote? Right, so if you look at the expression of R, the asymptote came about when 2 cos theta minus 1 tends to 0. So this happens when cos theta tends to half, which means that theta tends to plus or minus pi over 3. So which does make sense actually if you look at the diagram here, right? So this is when theta is tending towards pi over 3. On the other end is when it's tending towards negative pi over 3. So that gives us this domain, right, for R. Okay, so that's one way that you can look at it. I also have students who went by the formula, right? If you recall, we have R equals to EP over 1 plus E cosine theta, right, for this. So if you have gone by that, so your job is just to look for the E, the P, and then plug it in. So you will have a different form here. You will have R equals to 69 over 1 plus 2 cos theta. So if you've gone by that standard formula, you have a different answer from different looking answer from this one here. But in this case here, your domain, which will come from 1 plus 2 cos theta equals 0, will be in the second and the third quadrant, which means 2 pi over 3 and 4 pi over 3. So how is that so? Because if you have something that looks like that, right, then your graph, so that means you're looking at theta equals to 2 pi over 3 and theta equals to 4 pi over 3. So the problem is that why do the curve appear on this side instead? So the reason is because if you use this form over here, so just throw pi in. You just throw pi in and you find that this is 69 over 1 minus 2, which is negative 69. So instead of appearing here, your graph actually flips over there, which is your point Q, right? So therefore, the graph supposedly to happen here will all take on negative value because of the form, right? And appears over here. So which is correct too, lah, all right? If you have stated the domain as such. Yeah, so therefore, there are two different answers, different looking answers, lah. Okay, but the domain will make sure that the curve is unique. Yeah, all right. Okay. Yep. And the rest of it, okay, quite similar to what I've said. Try to capitalize on known point, like in this case, this point over here, right? The point A, already known because you're given the, whenever you're given the Cartesian equation, you can find the point, those focus over there. And apply just E, right? Definition of E. Okay, I don't even need to know the value of the directrix, yeah, because the P will, yeah, the P can be found actually. Okay, so I don't have much to actually emphasize for this. Yep. So there's this real application to the problem. Okay, I think based on the work mark, I think this part wasn't a problem. So the basically the time difference allows you to work out the 2a, right? The difference in the distance. Yeah. And right, okay. Is the next part. Okay, the next part of the question, which is to determine the possible position of the, so that means we know that the source of the sound will be actually on a hyperbola, right? If it has this kind of property, so your job is to work out the equation of the hyperbola, right? So the so-called the easiest or the nicest way to go about it is just to use mod d2 minus d1 using xy as the point on the hyperbola, right? So we have this, and then we unpack the square root so that we have this quadratic equation of the hyperbola, right? And because the hyperbola happens on, right, we have pinpoint that it is moving along the right side, so that's why we need to have the condition on x to be greater than or equals to 686. I think we're talking about this. I think this point here was 686. So that's why we have px to be greater than or equals to, or if you specify x positive, that's fine too, lah. So you're talking about this arm over here. Method 2 will be for people who who need to work out the a square and the b square, to, because basically they already have in mind this, right? This would be the equation. So your job is just to work out the unknown. So you already got a square, a from the previous working. So you just need to work out the b. So for the b, you will work it through e, because you know where the focus is and you know what a is. And then using this, you work out the b. So this is strictly applying formula to do the job, lah. So that's also possible. Yep. Whereas this first method, just use the geometrical definition, right? Okay, then the next part, not a problem, is to locate y when x is 1000. Yep. Okay, so the last part, the last question. Right. Okay, so again, geometrical problem. Question will typically guide you. They say by considering df2 minus df1. Right, so df2 minus df1. But we know actually fg, f2g minus gf1, right? We know this difference over here, right? So how do we consider df2 minus df1? So because you need to involve, so we have this property here, df2 minus df1 is equal to 2a. So the idea is to express, df2 as dg plus f2g. Okay, f2g is drawn on a big circle with a radius given by, right, a1 and f2. a1 is a vertex, f2 is a focus. So we do know that if this is a0 and this is negative c0, right, so the difference between them, right, will be a plus c. So we do know that the big circle has a radius of a plus c. Now the small circle has a radius of distance between the vertex and this focus here. So this focus is c0. So that will make the small circle having a radius of c minus a. All right. So therefore your DE, okay, so therefore your df2 will be equals to dg plus c plus a, whereas your df1 will be equals to de plus c minus a, right? So if you go with that, you'll be able to bring out dg and de in your working. So the difference is equal to 2a, so that will immediately, right? So we have that. Okay, so to figure out the radius, okay, and then take the difference, you'll find that it works out to be 0, right? After the cancellation is done. So we have this conclusion here that dg is equals to de. Yep. So that was how this first part was done. Okay, then the next part. Okay, hence or otherwise to prove. Yeah, so this question was about okay, sorry, we still have one more part here, right? To show that it is equal to c squared over a minus c. So for this next part, we will focus on, okay, so for this next part, okay, so for this next part, we will focus on the triangle DF1, F2, right? So DF1, F2, remember it was this, so this is F1, F2. So we know that this is A plus C and this is A minus C, right? So, okay, so we have, hold on, let me take a look where the D is. Oh, wait, the D is the point further up. Sorry, the D is up here. I got mixed up with G. So we are looking at this triangle here, right? So this is a right angle triangle. So this side here is C. Okay, so I think we are calling this a common length here, H. So this is C plus A plus H, and this here will be H plus C minus A, right? And then we know that this 2 will be 2C. So basically it's to use Pythagoras theorem, all right, to connect the three sides. Yeah. So that would give us, right? So that's how we ended up forming this. So I think once you simplified it, you will be able to find, basically what we want to find is an expression for H. So once that is done, you get H into this form over here. Okay. Then yep, so this is this part. Then the last part 2 of the question, okay, the question was about showing this result because we actually derive it from a geometrical definition, and we claim that a squared plus b squared is something positive, so we give it an expression called c squared if you recall the derivation, but this is proving it slightly differently. So how do you hence or otherwise prove c squared after you got the sides of h, after you got the values of h, right? Okay, so okay, so how to involve the b in the first place, right? In this question here, there's only one point that falls on the hyperbola, right? And that's the point G, right? So the point, okay, but find D by finding the intersection of df1 and the hyperbola. Okay, so there's only one point that falls on the hyperbola, and that is the point G, right? That is the point G. There's only one point that falls on the hyperbola. So it's not G, it's actually the point D. I got it mixed up again. It's the point D. So, and the point D happens when x coordinate is C, right? It's constructed above the focus. This is C0. So the only way I can involve B, right, is to actually consider the point D here. So at the point D, right, it satisfies the hyperbolic equation with x replaced by C. So we do know that D has got this coordinate here. So once you know D has this coordinate, you can actually plug it back into any of the equation that involve actually the length. So we have found df1, for example, to be de plus c minus e, right? That means we consider this length df1 to be de, right? Plus this, the radius of the small circle, which is c minus a. We just found this to be h. So once you plug it in and then you unpacked it, you'll be able to get c squared equals to a squared plus b squared. Yep. Okay, so yeah, the the geometrical problems in conics are not easy. Yeah, they're not easy, but if it does come out in the exam, right, it'll be much guided, right? So look into what the parts lead on to lah. Okay, read into the earlier parts, what result that can or what you can follow through from the results that were established. Okay, so yeah, that's all.